Good evening, everybody. Welcome to another session of Organic Chemistry Review. In today's session, we are going to review for the first exam, which is scheduled for next Tuesday, January 31st. And so we are going to get going right away. I noticed that we have a lot of students are joining us today. Okay, Christina, if your mic is working, can you go ahead and read this question for us?
Identify the reagents represented by the letters in the above reaction scheme. Choose reagents by entering the letters from the following table in the order that they are to be used. That is A, J, C, B. Do not include punctuation or spaces.
Okay, very good. So now what they want us to do is to identify these reagents here, this here, this here, this, and this. Each one of those reagents will be transforming each molecule to the next molecule. So let us do this together. What will be A? This here. What reagent do we need for A? Going from benzene to bromobenzene. Okay, then I said G. Okay, everybody got that right. Great. Say G. Very good. So this will be a good starting point for today's session. So that is G. So that is correct. In other words, going from benzene to bromobenzene, you need bromine in the presence of, this time, iron 3 bromide. Okay, very good. Now about the next one. What do we need for this here? Going from bromobenzene to nitrobromobenzene. Okay, we have C. Okay, is that correct? C correct. Okay, that is good. That is a nitration. We are performing nitration, which is C. Okay, so we are going to perform nitration. So the reagent for that is, of course, nitric acid in the presence of sulfuric acid. Very good. Okay, let's go to the next one. What do we need for C? Okay, I said D. Okay, C. What do we need? D. So what do we need to do here exactly? We need to reduce the nitro group to the amino group. So D, all of you say D. Excellent, excellent. Okay, so now we are going to use D. When you have to reduce the nitro group, you will use some kind of acid in the presence of ions. So, okay, so we have here, we could use any kind of acid, and that acid could be hydrogen chloride, hydrogen bromide, or sulfuric acid in the presence of iron. Okay, so far so good. About D, going from here to here, which is they want us to do sulfonation. F, okay, great. F, let's see what F says. Where is F? Okay, that is sulfonation. Okay, so you guys are rolling. Very good. So that is F. So that means we take sulfur trioxide in the presence of sulfuric acid. Okay, so folks, what we've just done now, we simply just doing a little bit of icebreaker so that we could get the session rolling. So in essence, you guys seem to know many of the reagents that we could use to perform electrophilic aromatic substitution reaction. Okay, very good. Now let us go to another problem here. So Stephanie, you are welcome. I notice you are joining us. Okay. Emma, go ahead and read this question for us.
Okay. Select the reagents you would use to synthesize the compound below from benzene. Use the minimum number of steps.
Okay. What they want us to do here, starting with benzene, this here, they want us to synthesize this compound here. Okay, without taking a look at the reagent, let us see whether we can do that. Okay, without taking a look at the reagent, let us see whether we can do that. Okay, what do we need to do here? What do we need to do? We need to form this hydroxy here attached to this methylene group. Okay, anybody has an idea the first thing we need to do here? Without taking a look at the reagent set. Okay, acylation. Okay, very good. So acylation. Okay, so you want us to do this? Because we only need 2 carbon atoms, right? So therefore, I'm assuming that you are suggesting that we do this since you say it is. Okay, do you mean acylation or alkylation? Okay, right now I am doing acylation. Okay, you mean alkylation. Okay, but okay, that's good. Okay, but anyway, I will come back to that. Let me just finish this acylation here. So with this here, you will need this, and then you need this here. Okay. Given the fact that we need to make this here, okay, what this suggests to me is somehow we need to make an alcohol, and to make an alcohol, we will need a carbon-carbon double bond, in which we could then make an alcohol using BH3 followed by hydrogen peroxide. So anyway, so let us see here. If we do this, we reduce this with palladium. If this is what we are going to get right here, I am going through this so as to just give you a little bit of some review. Okay, this will give you CH2, CH2. Okay, so if this is the compound you're going to make, then we might as well just go ahead and do the alkylation. Okay, we could simply do the alkylation, in which we do this. Not directly, we could do alkylation directly with this reagent here, followed by this. Okay. Do you agree with that? If you agree, okay, I see you guys are already giving me the, okay. But anyway, let us go through this. I see EJCK. Okay, let's see whether we could be correct. Let us see here. Supposing we now go from here, okay, keep in mind what we want to do here. We want to form a carbon-carbon double bond right here. And the reason why we want to do that is because we know we have to make an alcohol. And to make an alcohol, we need to add water in an anti-mechanical fashion. If you remember what we did last semester. Okay, so right now we want to now do MBS in the presence of a peroxide, any kind of peroxide we do, and that will give us this here. That will give us this. Is bromine here. And then once you get that bromine there, keep in mind that the MBS will replace and a benzylic hydrogen. This is a benzylic hydrogen. The MbS, this reagent here, will replace a benzylic hydrogen with a bromine atom, and that is what we have done here. So now, if we now take hydrogen peroxide or potassium hydroxide, we could now do dehydrohalogenation. Dehydrohalogenation to now form a carbon-carbon double bond. And once we form our carbon-carbon double bond, now we go to the last step, which is now step 1, BH3. Folks, do not forget those reagents that we used last semester, because as we progress during the course of this semester, we are going to be using those reagents, followed by peroxide, and therefore that will give us the product that they want. Is this here. Right here. Right here. Keep in mind that this reagent here, what this reagent does is to add water, the element of water, in an anti-mechanical fashion. If you look at this, we add in hydrogen here, we are then also adding OH here. Okay, now let us see the steps, whether we agree with what you guys have. Let us see here. We say we are going to do, okay, let us assume that we are using this, since we don't really need to use this right here. We don't need to use this, since this is where we want to go. Let us assume that we're going from here to here. Do we have this reagent here? Do we have this here? Where is this here? Is that E? Okay, good. So we do have it. Great. So that is E. Okay. So that is E. Okay, then we go to here. Let's go to the next one. Do we have MbS with peroxide here? Let us see. Do we have it? MbS with peroxide. Okay, yes, we do have it. By the way, this is a peroxide, this here. So we do have MbS with peroxide, and that is J. Okay, so that is J. Okay, so that is J. Then do we have, I know that you guys already given this to us. You say EJCK, that is ML. Very good. Now, do we have this here? Okay, do we have this here? Yes, we do have a C. And that is this. So that is our C right here. Okay, then finally, do we have the, yes, we have K right here. The borane, followed by hydrogen peroxide, and that is this here. Okay, and that is K. Okay, if you follow that, give me a happy face. If you follow that, give me a happy face. So, in other words, these two, the first two problems we've done here is simply just to give us a review of some of the reagents that you need to perform reactions dealing with aromatic molecules. Okay, now let us go to the problem set from the spring 2011 exam number 1. Let us go to that. Let me see here. Let's see. Where is this here? Problem. Okay. Oh no, that's not what I want. Sorry about that. Okay. Okay. Okay, then what I want us to do, do you guys have any preferred questions from exam number 1 in spring 2011? Do you have any preferred questions? This is question number 13, by the way. Okay, no preferred questions. So let us start with this one here. Julian, go ahead and read 13 for us.
The reaction below produced 3 bromo, 3 methyl, 1 butene, and 4 bromo, 2 methyl, 2 butene. Provide a mechanism that accounts for these products.
Okay, folks, we are going to get mechanism problems like this. Both mechanism problem involving conjugated systems, and also mechanism problem involving the aromatic, electrophilic aromatic substitution reaction. So, let us, how do we do this? The first thing we need to do here, we need to write this, know the structure of these molecules. Okay, we know the structure of this, and this one here. Okay, that's the first thing we need to do, write this structure of this. Okay, these are the 2 products. This is the reaction right here, and these are the 2 products. So let us write the first product. Say 3 bromo, 3 methyl, 1 butene. What is the base name here for this here? 3 bromo, 3 methyl, 1 butene. What is the base name? Butene. Okay. So we have butene. Let me change my pen. So if that is what we have 4 carbons. 1, 2, 3, 4. 1 butene, so double bond is here. And the 3 position, if this is carbon number 1, carbon number 2, carbon number 3, so we have bromo here. Also on carbon number 3, we also have methyl. Okay, that's all we have here. So let us complete the rest of the molecule. CH3 here. Of course, hydrogen will be here, and 2 hydrogen will be here. Okay, this is one of the products. And then the other product is this, 4 bromo, 2 methyl, 2 butene. Once again, the base name is butene, so let us write that. 1, 2, 3, and 4. Okay, now they say 2 butene. So this is carbon number 2. We place butene right here, the double bond here. And then 4 bromo, if this is carbon number 1, 2, 3. Okay, this is 4, so we have bromine here. And then they say 2 methyl, so the methyl is here. Okay, methyl is here, so let us complete this molecule here. I tell you what, I don't want to confuse you. Let me write it, let me number from this other side. Okay, let's make this 4. Let us make this 4. This is carbon number 1, carbon number 2, 3, and 4. Okay, bromine is here. And then they say 2 methyl, 1 and 2, so methyl is here. Okay, now let us complete the molecule. CH3 here. Okay, you need hydrogen here. And here we need 2 hydrogen here. Okay, these are the products. Okay, what he wants us to do is to provide a mechanism that will account for the formation of these two products. Okay, does anybody know the first thing we are going to do? What is the first thing we are going to do here? Reacting this with this double bond attacks hydrogen. Okay. Which double bond will attach the hydrogen? Okay, will it be this double bond? Let us call this one double bond and two. Which one? Is it the one double bond or the two double bond? One double bond. Excellent, excellent. Okay, that is correct, but why? Can anybody tell me why it is this double bond that will attack? Most stable carbocation. Excellent. Okay, will somebody ask a question for me? Somebody is asking me a question. Okay. Anyway, I don't see this person here. Okay, anyway. The reason why this double bond will attack is because you will form the most stable carbocation. Keep in mind, folks, that is the essence of all carbocation reaction. Anytime you are going to form a carbocation, if you have a choice of formation, always the most stable carbocation will be formed before anything else. Okay. If that happens, so we are going to get this intermediate. Keep that in mind. The most stable carbocation will always be formed. We have that. Then we have this. Then we have this. Methyl is here. Another methyl is here. And then the carbocation is here because this hydrogen here is coming from here. Okay, of course we know that bromine is also formed. Okay, now what happens? Keep in mind we want to explain this product and this product. Now what happens? Okay, what happens? Can we explain this product from this here? Can we explain this? Yes, okay. So if we say we simply just take this, so we have this here to attack this, and therefore that will give us the 1,2 addition product. So this is the product of a 1,2 addition. So we have explained that. Now how do we explain this? How do we explain this? That this is the 1,4 addition. Okay? This is 1,4 addition, okay? Carbocation rearrangement because it's conjugated. Excellent, great. Resonance, great. Both of those are correct. So now let us draw the resonance for this. Let us draw the resonance for this here. This is the symbol for resonance. So in so doing, okay, let us, so we don't confuse ourselves, take this out of here. So now the resonance, we are going to move the pi electron to here. Okay, once we do that, then we get this resonance structure. Positive charge will be there. Now the carbon-carbon double bond will be here. Right here. That positive charge is now gone, so this CH3 is still there, and this CH3 is still here. Okay, now what is going to happen now? Can we now explain the formation of this product? What happens next? What happens next? Can we explain how we get this? What is going to happen now? We have formed this carbocation now as a result of resonance or rearrangement. So what are we going to do next to get this product? Bromine, the bromide attacks the carbocation. Excellent. Because the bromide is a nucleophile now. Okay, so this comes in here, attach this, and then you form this product. So now we have explained the formation of those two products, and that is what they want us to do. They gave us the reaction And of course, they also gave us the product in the form of the names of the product, and then we write the structures of the products, and then from there we write the mechanism. Now, if you agree with what we have done so far, give me a happy face. Okay, that is clear to everybody. Good, good, good. Okay, very good. Good. Okay, good. Okay, so we are moving right along. So now, still on the exam number 1 of 2011, let us go to... No, we did that already. Let's see. Okay, good. No, we did that already also. Okay. Okay, we did not do this yet. Let's do number 10. Okay, Julian, go ahead and read this question for us.
What products would you expect to obtain from the following reaction?
Okay, what products would you expect to obtain from the following reaction? Okay. Okay, this should be fairly easy also. Okay, let's start with this. What product do we expect here? What is happening here? What is happening here? Okay, okay, reduction. Reduction of what? Very good. You have the right benzene with, okay, excellent. Reduction, okay. Reduction, we are reducing. In this case, we are going to reduce the carbonyl. And the carbonyl that is attached to benzene is always reduced by this reagent. And also, we are also going to reduce the nitro group. Okay, so the product that we are going to get will be this product here. Keep in mind, all of this here as essentially just knowing your reagents. Okay, so these are fairly simple processes, just knowing your reagent. So this becomes a CH2. Of course, you have CH3 attached to that. And then this becomes your amino group. Okay, is that clear to you? If it is, give me a happy face. Okay, great, great. Okay, good. Now let us do this here. B. Let us do B. Okay, what is happening with B? What is this first step here? The first step is what? What kind of reaction is this? Nitration. Okay, great. Great, great. Everybody say nitration. And then the next step is what? The next step is what? This reagent. Reduction. Okay, good. Okay, so now, since you guys agree that we are going to do nitration first, and we have here bromine, 2 bromine atoms here, we know that bromine is what kind of director? What kind of director is bromine? Auto para director. Okay, so very good. So therefore, we will expect to get this product. You will expect to get this product. You have bromine here. Another bromine here. Now, because this is auto para director, we will expect to get para to this here, right? It will be just nitration. Okay. Now, if we get para to this, it will be the same product because this is a symmetrical molecule. And the other product we are going to get will be the the auto product. We also obtain this. The bromine is here. Another bromine here. Now we're going to now have the nitro group. Auto to, oh, okay, cylinder green is giving us YouTube stuff to watch. That is good. Very good. So, Shilanda, is that nitration in that YouTube? Okay, so now you have the nitro is here. Okay, so right here, of course, we are doing nitration followed by hydrogen and sulfuric acid. Okay, so now the next step is what? The next step is this here. Let me change my pen. The next step is this. Iron and some acid. Okay, you guys said we are going to do the reduction, so we reduce this here. Okay, so that gives us, change my pen. Okay, we do this one first. So we have bromine, and we have the amino group. That's what we get. And for this here, we also get the same thing. Bromine, we have bromine, and then we have the amino group. Okay, is that clear to all of you so far? If it is, give me a happy face. Okay, good, good. Okay, now let us do this one here. Let me remove the clutter here. Take this out of here. Okay, let us do this. Okay, what do we expect to get here? Oxidation. Okay, oxidation. Okay, that's Patrick. Very good. Okay, what are we going to get with this oxidation? This reagent, we have two alkyl group attached to benzene, 2 carboxylic acid. Excellent. Excellent. Okay, so we are going to clip that molecule and we obtain 2 carboxylic acid, just as we say that and that. Okay, very good. So now let us do the next one. Take this one out. Take that out. Okay, let us now do this. This here. What do we get here? What is going to be the product here? What should we expect to get? Okay, what do we expect to get? Okay, okay. How many people say, yeah, it is alkylation? Okay, we have 2 choices. We are going to get either propyl alkylation or isopropyl alkylation. Okay, it is Friedel-Crafts alkylation. Okay, okay. If you think we are going to get propyl alkylation as the major product, give me a happy face. No happy. Okay. If you think we are going to get isopropyl, give me a happy face. Okay, good. Okay, but that is correct. It is isopropyl, even though we are starting with propyl chloropropane. Even though we are starting with this, we are going to get the isopropyl product. But why? Does anybody know why? Can you give a mechanism for that? Anybody know why? Why are we more stable carbocation will be on the secondary carbon? Exactly. So if you remember, whenever to form the, let me take this out of here. For this particular reaction here, whenever you are, if you want to perform a Friedel-Crafts alkylation, okay, in this case we are starting with propyl chloride. Keep in mind to generate the electrophile. Okay, what the first thing that happens is the aluminum chloride is a Lewis acid. It will draw the chlorine to itself, and in so doing, it will break the chlorine carbon bond such that you have this here. That is the first thing that happens. And in so doing, we form a primary carbocation. We form a primary carbocation. Keep in mind, primary carbocation will rearrange to form the more stable carbocation. Keep that in mind, folks. Okay, that is very, very important. So now we form a primary carbocation. Primary carbocation. Now this carbocation will rearrange to form a secondary carbocation, and the way it will do that, this hydrogen will shift. So we have what we call the hydride shift. The same thing, we could have an alkyl group shifting. Okay, we call that the hydride shift. So the hydride will shift and taking the electron with it to come here. So now you are going to form the secondary carbocation. Okay, remember, anytime your initial carbocation, if it is possible for it to rearrange to form a more stable carbocation, that will happen. That rearrangement could be in form of hydride shift or alkyl shift. Okay, so I say alkyl shift. That is also possible. The alkyl could be a methyl group, a propyl group, any alkyl could shift. Okay, so now we form, at this point, a secondary carbocation. Okay, now it is this secondary carbocation now that will react as your electrophile. It is this that will react as your electrophile. Okay, now that is why, so now let us now draw this product. Let me take all of this out of here. We know how we form this now, okay? It is now the secondary carbocation that will react as your electrophile to now give you this product. Okay? Now, before we get the product, where do you think this electrophile will come? Will it come here? Let me number this. Let me say this is 1. And let me say this is 2. Okay, will it come to position number 1 or position number 2? Okay, just go ahead and give me a text message. Will it come to position number 1 or 2? 1. Okay, what? That is correct. That is correct. Why 1? Why 1? Because of the methoxy group. It's more reactive. Okay, the methoxy group is more activating than the chlorine, and therefore it will assume the direction of the incoming group. It will take over the direction of the incoming group. Very good. Okay, so therefore our product will be this here. Our product will be, at least the major product will be this here. Chlorine is here. Of course, we have this, we have this, we have this. We have the methoxy group here. And then we have the isopropyl group right here. Okay, that will be the major product. Okay. Now, it isn't to say that you are not going to form a product in which the propyl is there, but the major product will be this one here. Okay. Okay, is that clear to all of you? If it is, give me a happy face. Okay, good. Okay, I think we finished the problem on this page. Now, let me give you this. Let me now give you a little bit of the similar problem that we did last night. Supposing I give you this. Supposing I give you this. You guys are going to do this now. I do not plan on doing it for you, so we are going to do this together. Supposing I give you this. And I say I could use any acid. I could use HCl, or I could use HBr, or I could simply just say this here, or I could use sulfuric acid. Now, if anytime you see this, anytime we use this hydronium ion, that means that it could be any one of these. Okay, it could be the hydrogen chloride, bromide, or sulfuric acid, or even sometimes nitric acid. Okay, supposing I give you this. Okay, let's just use one of them. Take the rest of them out. Say we use this. And I say we have this product. And I say we have this product. What I want you guys to do now is to give me the mechanism of this, that transformation, mechanism. Give me the mechanism of this transformation. Okay, how do I start doing this? What do I need to do first? Let's see, is there a question here? What way did you say the regular propyl will... Yes. Yeah, I did say the regular propyl will form also, but it will be the minor product. Okay? Okay, okay. Now let us do this. Okay, how I need the mechanism for this. What is the first thing that is going to happen? What kind of analysis do you want to do here? Okay, if you take a look at this, okay, this carbon is this carbon. Okay, and then this carbon here, that is the analysis that you need to do, is this carbon. Okay, so what does that tell you about those two carbons? What is going to happen to those two carbons? I mean, to those carbons before this reaction takes place. What is the first thing that will happen? The first step of this, okay, they become carbocations. Excellent. They become carbocations. So for them to become carbocations, so that means we are going to have this, right? This attacks this here, right? So we have HCl here. And of course, we could say that this one here attacks this here, and of course this will break. And where would the carbocation be? You already told us the carbocation will be here. So that means it will be here. So that means we are going to form the secondary carbocation. Okay? So therefore, what do we have? We are now going to have this. Okay, do you see that? Okay, so now you form, because this is a CH3 now. Don't forget, this is a CH3 right here. And this is also a CH3. Okay. Now, do you now see how this could happen now? So what is the next thing that will happen? Once you form this carbocation, What is the next thing that will happen? I'm simply just going to give you the product. I will assume that you will be able to draw the reaction mechanism. So at this point, the benzene will react with this. I will simply place benzene here. You guys should be able to draw that mechanism. So now you form this. And then you have this. Okay? Now, what is going to happen now? Because we need to go here. What is the next thing that will happen now? What is the next thing that will happen? They become, okay, okay. So, yes.
Professor Rende, after the benzene and the first carbocation bond, wouldn't that double bond go away, and there should be a positive charge on that bottom carbon of on the bottom right carbon of the benzene? No, on the benzene.
This here?
Shouldn't that double bond be gone because it just was used to form the bond between that and the other carbon?
No. I told you I'm not writing the mechanism. I'm simply giving you the final product. What I'm telling you to do, that you guys should work out the mechanism yourself. Because this is just the electrophile, right? So, okay.
But I mean,
so
I just don't get how the positive charge isn't there anymore. Like, that double bond should be gone, shouldn't it? The one on the benzene.
Which double bond? Okay, but you are looking at the mechanism. I'm looking at the final product. Okay. In other words, you want me to draw the mechanism. Okay, let me go ahead and okay, let me go ahead and draw the mechanism. So, what you want me to do now? Let me take this out. I was hoping that you guys would say that you follow this and I don't have to draw this. I was trying to be to save some time. I know you guys want to go home and rest for the day, right? Okay, so we have this. This comes here. Attack this, right? Once it does that, of course we know that we have, let's do this, right? We have hydrogen here. We also have hydrogen here. Okay, so that will give us this here. That's what you are asking me. But what I was doing was simply just giving you the final product. Okay, so this double bond is still here. This double bond is still here. And now we have this here is now attached to that carbon. That is still there. This is here. This is here. This is here. This double bond is still here. Now, we also have this hydrogen is here. The positive charge is here. Is that what you are asking me?
Yeah, that was. Thank you.
Okay, but in this case, we are going through the mechanism now. So, at this point, what is going to happen? We're now going to have keep in mind that when you form this, we also generated right here a chloride. Okay, this chloride will now act as a base. Okay, and pull this proton from here. So we are going to regenerate the aromatic system. Okay, and once we do that, and then we're going to get the product that I gave you earlier. We now have this, we have this, we have this. Now you're going to have this. Okay, do you see that? Plus, of course, once this chloride pulls this hydrogen, it becomes HCl. Okay? Okay, if you see this, give me a happy face. Okay, I see Lorraine, Brea. Okay, great. So, in other words, what I was doing, I wasn't giving you the mechanism. I simply gave you the final product. Okay, go ahead.
Wait, is mechanism finished? Because it's different than the one that you drew originally.
No, this is the one I gave you before you when you were asking the question. But that is not the final product.
Oh, okay,
this
sorry.
Is where
I wasn't
we're
sure if we were done.
This is what this is what I want you to explain. Now, what is going to happen now? We see have a HCl here. What is going to happen next? What is the next thing that will happen? Because we see have to join. Don't forget, we still need to join this carbon to here. Okay? Okay, so what is going to happen? Double bond attacks again, okay? Double bond attacks again, exactly. That is correct. The double bond attacks again. So, now we go through the process again. So now this double bond now, okay, let me make it a little easier for us to see. Let me take this out of here and put it right here. And put it right here. Okay, so the double bond attacks again, which means that we are now going to get this. This now comes in here again, attacks this, and this breaks away. Okay, now what we have, we have. Do we know what what are we going to get now? What are we going to get? Can we do? Okay, what are we going to get? Okay, another carbocation, exactly. You form another carbocation. Good. Somebody say, can we do number 8? Yes, we will try that. Okay, so now we have this here, this here, this here, this here. Because now this is a methyl group now. Okay, this because the hydrogen goes here, and the carbocation is a secondary carbocation, and of course we have this here. Okay, now what happens next? What happens next? What happens next? At this point, should I just go straight to the product? I skip the mechanism. Okay, what is no? Yes, I get no and yes. Benzene attacks carbocation. Exactly, good. The benzene attacks the carbocation. The double bond, the pi here attacks the carbocation. Keep in mind, this is here is an auto director. I mean, auto para director. So comes here, attacks this, and then we form our intermediate again. Form our intermediate again. This here, okay, since you guys want me to go through the mechanism, we now have this here. This is now joined. This is here now. This is here now. And now, this carbon now becomes the carbocation. Keep in mind there is hydrogen here. Okay, so that hydrogen is still here. Okay, so at this point, what is going to happen now? What is going to happen now? Keep in mind, we also have, when we form the carbocation, we also have the chloride. Okay, so what is going to happen? What will happen next? Okay, we have this intermediate here. So what do we expect to happen? Okay, the chloride pulls off the hydrogen again, exactly. And then you form this. And then that is gives us our final product. Let me take all of this out of here. So that gives us our final product, which is going to be this here. Okay, so now what have we done? We have not explained or given the mechanism for how the benzene, this benzene here, reacts with this molecule here in the presence of some kind of acid to form this molecule here. Okay? Okay, so you see that. Now, supposing I want to make this interesting. Supposing I want to make this a little bit interesting, right? Okay, let us say that I want to now extend this. I take this out. Take all of this out. We know how to do this now. Supposing I want to give you guys a little bit of a challenge so that you now put on your critical thinking skill. Okay? Supposing I say to go to here. To go to here. Okay, I have this here. Okay, supposing I wanted to go from here to here. What will you do? How can we do that? Anybody has an idea? Okay, going from here to here. Okay, pull up the idea. Oh no, that's the last one. Okay, supposing we have MBS. Okay, in the presence of peroxide. Okay, so that will give us this. Okay, that will give us that. Missing, you said missing 2 on the oxygen. Oh yeah, the peroxide, thank you. Okay, so supposing I have MBS in the presence of peroxide. Okay, so the first thing that happens is this here, and then from here we could go to here. Where is number 8? That's number 9. We did that already. Oh, number 8. Okay. Okay, number 8. That's a good one. Let's see here. Kia, go ahead and read number 8 for us.
Propose a structure for a compound with formula C9H12 that only gives 2 monochloral compounds, C9H11NO2, when it undergoes electrophilic aromatic substitution reaction. Write the structure for the product C9H11NO2 and write the reagents needed for the reaction.
Okay, very good. Okay, so what we need to do here is to determine the structure. Of course, let's see here. Okay, we have this compound, C9H12. Okay, and they say it only gives 2 monochloral compounds. Oh, okay, they made a mistake here. 2 monochloral. Upon undergo electrophilic. This is supposed to be chloro, not NO2. Anyway, this is so. Let us simply change this to this is supposed to be chlorine right here because it's 2 monochloro. This here, okay. And we write structure for the product. Okay, this is supposed to be chlorine. Okay, and write the reagents that you need. Or you could also use the nitro, but let's take chlorine. Okay, so the molecule we have is this here, C9H12. By the way, I believe this problem is from your book, the back of your book. So if that is the case, what is the index of hydrogen deficiency? That is the first thing you need to determine here. C9H12, what is 4? Index of hydrogen deficiency is 4. IHD equals to 4. If IHD equals to 4, okay, anytime you have IHD equals to 4, now since we are dealing with aromatic compounds, I would say that we already have benzene. Okay, I would take a very good guess that we have benzene, since they also told you that it is we are performing electrophilic aromatic substitution. So definitely it is benzene. Okay, so benzene has taken up 6 of the carbons. So we only have 3 more carbons to go. So therefore, the question here is this molecule going to be this here? Because if you have 3 more carbons to go, those 3 more carbons will have to be either methyl, it has to be methyl and ethyl. Do you follow that logic so far? If you do, give me a happy face. Okay, okay. Now, or it could be this, okay? Keep in mind, they say that this compound only gives 1 monochloro product. Okay, or could it be this here? Okay, or the other choice is, let's look at the 3 choices that we have. Or could it be this? Those are the choices. Now, keep in mind what they are telling us that is that when you perform chlorination on this compound, okay, on any one of these, you only form, how many? 2. You only form 2. Okay? Now, if we perform chlorination on this here, let us see how many products do we expect to form. This is an auto-para director, right? Okay, so what do you think we are going to form? So we have this, this here. Okay, we could form a product here. Let's put chlorine here. That would be 1 product. Or it could be this. Because that would be para to this, para to this and auto to this. Okay, this here. Okay, it could be this here, right? Okay, that is a possibility, right? Okay, those 2 products could be formed. We have this here and this here. Or, in this case, even though it would be a minor product, it could also be formed. Keep in mind, it is a minor product, but it could also be formed. Because they are not telling you whether it is major or minor. They simply say it only form 2 products. Because these are auto-para director, this would be a very minor product because generally you do not want to place anything here. These 3 products are possible if it is this compound. So therefore, what are we saying here? Would compound A, if we call this compound A, will compound A be this molecule? The answer will have to be no. Okay, now let us take a look between compound this here. Let us now say this is B and C. So what will it be between B and C? Okay, let us look at what we have here. What will it be? Okay, Emma said B. Okay, do you agree with Emma that it is B? Okay, okay, yes, yes, okay, very good. If it is B, let us see what we get with B. If it is B, the chlorine comes here, right? Okay, let me just take this out. Okay, if it is B, what are the products we get? We get one product here. Okay, these are auto palette directors. So, whether it goes here or here, it is the same product. Because this is symmetrical. And the other product will be, if we have this here, okay, will be here. Whether it is here or here, it will be the same product, okay? So here, okay? So therefore, if we choose B, B will only give us 2 monochloro products. So therefore, the answer has to be B. But just for the sake of this discussion, let us look at C. What happened with C? Let me make some room here. Okay, so we say the answer is B. So what happened with C? Okay, let's see here. It could form chlorination. Okay, chlorine could go here. Okay, that's one. That's a auto position to. Oh, it forms 4 products. Okay, Patrick already told us. But just for the sake of this discussion, this exercise, to show everybody what this is. Okay, Patrick said 4 products. Let us see whether Patrick is right. So we have that. We have this. We have this. Let's use the red pen. So we say we have this. Okay, 1 monochloro product. Let us see another one. Okay, so we have this here, we have this is still here, and then we say, if it is on this side, that's another product, okay? So now we could also have a product here, so that is 2, and then we have this, I think Patrick is right. Okay, we have this, okay. We have this here. Okay, so if we have, since they are also parallel directors, parallel to this, we have this, because that's parallel to the AT group. And finally, we have the 4th one. Okay, so we have the 4th one. Okay, okay, then that 4th one will be parallel to the methyl. Okay. Okay, so therefore it cannot be this here. So the answer is B. Okay, very good. So before we leave, I think, what time is it? 9:12. Let me give you one more problem here. See whether you guys can work on this.
Dr. Arende.
Yes, supposing I ask
Some people are asking, why can't
yes,
propyl group be a substituent on the benzene ring?
Okay, okay. Well, let's go back to that problem. Where was that? What is this? No, not that one. Oh, no, no, no. Oh, that's the last one. So, oh, I'm trying to find where that was. Okay, let me just take a new one. Okay, why can't it be propyl? Let us see. Can it be propyl? That's a good question. I wasn't even thinking about that. Okay. Okay, that would be, that is a legitimate question right here. So, what do we have here? Supposing we have the chlorine is here. Okay. And then, if it's here or here, it's the same thing, right? Okay, it could also be that. That is correct. It could also be propyl, yeah. Yeah, it could also be propyl. That would be consistent with the data that they're giving us. We could also, yes, that would be correct, Bray. Okay. Yeah, because this is an auto para director, so we have the auto and the para. Yes, this also could be correct. The propyl could be correct. Let's see, where's my pen? Okay. Okay, now let us now go, before we leave. Oh, by the way, there was one thing, there was a problem I gave you earlier. I want to go back to that. I was just thinking about that. This here, I told you, this reagent is for dehydration of alcohol. So let me take this back, okay? Emma, you are right. We need to use potassium hydroxide here. This should be potassium hydroxide. The phosphorus oxychloride, it is used to dehydrate an alcohol, not to remove bromine. Okay. Okay, supposing I give you this here. Okay, this is a synthetic problem, and I want you to go from here to here. And then we have iodine here, and then we have right here. Okay, give the synthetic scheme. Provide a synthetic scheme. Keep in mind, when we say give the synthetic scheme, you don't need to give the mechanism. Okay, so how do we go about doing this? Oh, okay, I see the question that Dimitris asked. Okay. Okay, okay, very good. I see some answers coming. So you want us to do alkylation first? Okay, if you do alkylation, I'm not saying that you are right or wrong here. I'm simply following your steps. Okay, ACL. And then we follow that with, let's go step by step. Give us a change, a chance. Let's go step by step. Okay. Okay, if I do that. Okay, so what is the next step? What is the next step that we need to do now? You guys are laughing at each other. Okay. Okay, acylation. Acylation is correct. Okay. Simone said acylation. Acylation is correct. Okay, because if you do the alkylation first, there is no way you will be able to introduce the iodine here. You cannot do that. Okay? So therefore, the first thing you need to do, because of this relationship here, the iodine is an autoparadirector, this is an autoparadirector, and the relationship between them is meta. So therefore, it will be very difficult to introduce the iodine once you have this in place. Keep in mind that the sulfonic acid group is a meta director. So therefore, the synthetic strategy here, you got to look at the substituent and then look at the way this would direct incoming groups. So the answer to this will be, let me take my eraser. So we have to start with acylation first. We start with Friedel-Crafts acylation. Friedel-Crafts acylation, and that will give us okay, so once we do that, what is the next step? Okay, you don't want to do sulfonation now because this is a meta director. Okay, then you want to do iodination, exactly. Okay, and the reagent for iodination is this here, copper 2 chloride. Okay, so you do iodination, and that will therefore introduce the iodine in the meta position. So you want to situate the iodine in the correct position before you reduce the carbonyl. Okay, so this is still here. This is here. Okay, Christina is having problem with her internet. She keeps going in and out. Okay, and then this will be here. Okay, now at this point, what do you do next? What do we do now? Okay, what do we do? Hydrogenation, exactly. We want to now do hydrogenation. Okay, we want to do hydrogenation. Now we do hydrogenation. Hydrogenation. Let's use hydrogen and platinum, or you could use palladium also. So now that gives you. Iman Boston is joining us. Iman, you have to watch the video later because we are almost closing the session now. Okay, so we have this. Now we have this here. We have this. CH2, CH3. And then at this point, we now go to sulfonation, because now this is a paradirector, autoparadirector. This is also autoparadirector. Right, okay, so now we're now going to, oh, I didn't know that, I didn't know you've been here before. I'm sorry about that. Okay, so now you do sulfonation. Sulfur trioxide in the presence of sulfuric acid. And that will give you now this product. Okay, is there any question on this? Okay. Okay, go ahead, ask the question.
I wanted to just know if, how do you find out which reagent goes first? Like, you know, chlorination or bromination through the experiment. I don't know which one goes first. How would you know? Is it by the directing?
What? Yes, by the directing. You got to look at what are the directors, okay? If you have this relationship you have is a meta-director relationship, and then you know that you need to introduce a meta-director first. But it depends on the situation that you have. In this particular instance here, we know that this ethyl and the iodine, they are metal to each other, okay? But then you know that if you simply introduce the ethyl right away, ethyl will not direct to the metal position. It will direct to the para position. So that tells us that you need to have a metal director here, which will be your carbonyl, the ketone. So that is why we made the choice to do the ketone first, to do the acylation, and then after the acylation, then you do your iodination. So this now will direct to this metal position, and then you reduce the carbonyl to a CH2. Somebody also asked a question: what's the difference between? Okay, what's the difference between? Oh, okay, one is the one with the carbonyl, that is acylation. And the one with the ethyl, that is alkylation. Okay, that is different. The alkylation is essentially just this here. You have an alkyl group attached to the chlorine. In the acylation, you have a carbonyl attached to the chlorine. Okay, this group here, anytime you have this kind of group, and an alkyl group attached to the carbonyl, we call that an acyl group. We call that an acyl group. And that is why we call this acylation. That is where the acyl comes from. Of course, this group here is called an alkyl group, and that is where the alkylation comes from. Okay, we call this the alkyl group. And that is where you get the alkylation. Okay, so that would be the difference. Somebody also asked a question. I forgot what the question is now. Why don't we do the reduction of the do this reduction before the carbonyl reduction before something? I don't know what that question is. But if you still remember the question, you might want to pick up the mic and ask me that question again. Okay, I know that question I see. I just wanted clarification in the, and they are both going to add. Oh, okay, I see. You are asking why can't we? Okay, let me go to a new page. The question that is being asked here, I think that's what we did earlier. The question that you are asking, how come we can't simply just start with the alkylation? Okay, you're saying that why can't we just do this? Do the alkylation, right? And if we do that, that was what I was trying to explain to, I believe that was Demetrius. If we do this, we get this product here. But that would be, oh, I'm sorry. But that would be a problem because keep in mind, this is the product that we want to make. This is the product we want to make. Now, if you start with this, there is no way you will be able to introduce the iodine, because this is an auto para director. If you now want to introduce the iodine, as we did, if you do this iodine here in the presence of copper 2 chloride, the iodine will go to the para position. And that is not what you want. The iodine will go to the para position, Okay? Keep in mind what we want is to have the iodine here, which is here, and then later on to have the sulfonic acid group in the para position. Do you follow that? So that is why we cannot use this process. Okay, so that is why we went to this route. We make this one first. We did the acylation first. And then from the acylation, then we could now do the iodination, because that will now introduce to the para position. To the meta position. That will now introduce to the meta position. Okay? And then once we do that, of course this will not work, so let us take this out so we don't confuse anybody. So now once we do that, we could now simply now do our sulfonation. And that is why we did that, okay? Okay, is there any more questions before we leave for today? It is about 9:30. Any question before we leave? Okay, folks, I will be around on Monday. If you have any more questions, I will be in the office, so feel free to stop by the office. I would say anytime after 12 p.m. on Monday, I will be here. And the same thing, I will also be here, of course, on Tuesday before the exam. Okay, Deadline is asking, what is the answer to question number 4? Question number 4. Let me see here. What is question number 4? Oh, the answer to question number 4. Oh, okay, that's a good one. Okay, let us see. Deadline asked the question number 4. Where is that here? I think I have it here somewhere. No, not that one. Okay, this one. Yes. So Deadline is asking us what is the answer to this. Okay, that needs a little bit of explanation. The answer to that is this one here. You say let's see, I'm not. Lorraine, go ahead and read number 4 for us. I think we have 2 Lorraine here. One of the Lorraines, go ahead and read number 4.
On mononitration HNO3 H2SO4, which compound would yield the highest para to ortho ratio?
Okay, great. That was Lorraine Bolden. Okay, good. Now, the answer to that is this here. I will tell you why. Okay? Now, when you have, keep in mind, we tell you, this is, all of these are auto para directors. Let's start with this. It's a good question, by the way. Okay, so we start with the toluene. Okay, let's start with the toluene. Okay, if we do nitration, we know that will give us a nitro, so we are going to get 2 products. Get 2 products. One is auto, and the other is para. So we have the para product. Okay. Now, remember I told you, for the auto para directors, always, the para product is always going to be the major product because of the steric hindrance. Because of the steric hindrance, in the auto relationship here. Steric hindrance simply means they will be bumping into each other. They have less chance of bumping into each other in the para position. So the para is always the major product. So that is the question they're asking you. Okay? So this is the minor product. Now, if you notice, now they're now increasing the size of the substituent, so they now go to ethylbenzene. Okay, the bigger this group is, the less the auto will be, because that will be the bigger steric hindrance. So now the next one, they now go to the isopropyl. Okay, so methyl is smaller than ethyl, so therefore there will be less auto product here, because there will be more steric hindrance. Now the isopropyl is bigger than the ethyl, so the auto product will be less. Now finally, exactly, because of a larger substituent. So we chose tertiary butyl because that is the largest of all the substituents. Okay? And because of steric hindrance, most of the product will go to the para position. So now you are, this is the tertiary butyl. Okay, benzene. Okay, so that is why benzene, that is why we chose this here, because this here is a case in which most of the product will be in the para position because of the larger substituent, just as Kia just said. The bulkiness of the tertiary group pushes most of the product to here. Okay, do you follow that? If you do, give me a happy face. Okay, good. Good. Okay, good. Good. Somebody has a question? Okay, if there are no other questions, sorry, that was okay. That's fine. I will post this webcast tomorrow morning. Because at this point I want to go home. I'm getting a little tired. I'm going to go home, and then tomorrow morning I will post the webcast. So hopefully by 12 p.m. tomorrow, this webcast will be available so that you guys can begin to use this to study for your exam on Tuesday. Okay, if there are no more questions, I will say enjoy your weekend and make the best use of the rest of the evening.